Somewhere in the galaxy right now, there is an object roughly the size of a city, spinning hundreds of times per second, containing more mass than our entire Sunday. A single teaspoon of its material would weigh about 1 billion tons on Earth. This is a neutron star, the second densest known object in the universe, surpassed only by black holes. It forms when a massive star, far larger than our Sun, ends its life in a supernova, and its collapsing core crushes down under its own gravity until protons and electrons are forced together into neutrons, packed edge to edge with almost no empty space between them. The result defies ordinary intuition. A neutron star typically measures only about 20 kilometers across, comparable to a mid-sized city, yet contains 1 to 2 times the mass of our entire Sunday. Gravity at its surface is so extreme that an object dropped from just 1 meter up would hit the ground at a meaningful fraction of the speed of light. Neutron stars are strange enough on their own, but the most remarkable discovery involving them did not come from studying one alone. It came from watching 2 of them collide, an event that solved a decades-old mystery about where some of the heaviest elements in the universe, including the gold in your jewelry, actually come from. In 1967, a graduate student named Jocelyn Bell Burnell, working with a radio telescope in England, detected an impossibly regular signal from deep space. A radio pulse arriving with such mechanical precision that some researchers initially, half-jokingly, nicknamed the source LGM-1, Little Green Men, wondering if they had detected an artificial signal. The true explanation turned out to be almost as remarkable. A rapidly spinning neutron star, called a pulsar, sweeping a narrow beam of radio waves around like a lighthouse as it rotates, with the beam sweeping across Earth's detectors once per rotation, producing that impossibly regular pulse. Bell Burnell's discovery opened up an entirely new category of astronomical object. Thousands of pulsars have since been cataloged across the galaxy. Some neutron stars are stranger still. Magnetars carry magnetic fields trillions of times stronger than Earth's own. So powerful that, according to some physics calculations, a magnetar located roughly halfway to the moon could theoretically erase the data on every credit card and hard drive on Earth. Starquakes on magnetars, sudden readjustments of their crust, have released bursts of energy detectable across the galaxy in a fraction of a second. And because pulsars are so precisely regular, astronomers now use networks of them as a kind of galactic GPS, and even as detectors for gravitational waves, ripples in spacetime itself, predicted by Einstein, that very slightly alter the timing of pulsar signals as they pass through. For a century, Einstein's theory of general relativity predicted that sufficiently violent cosmic events should send ripples through the fabric of spacetime itself, gravitational waves, stretching and compressing space by an almost unimaginably tiny amount as they pass. For decades, detecting them directly seemed to be at or beyond the absolute limit of achievable technology. That changed in 2015 when the LIGO Observatory, using laser beams split across perpendicular arms each several kilometers long, sensitive enough to detect a change in length thousands of times smaller than a single proton, directly detected gravitational waves for the first time from 2 colliding black holes over 1 billion light-years away. The discovery earned the Nobel Prize in Physics and opened an entirely new way of observing the universe, one based on spacetime itself rather than light. 2 years later, in August 2017, LIGO and its partner observatory, Virgo in Italy, detected something different: gravitational waves from 2 colliding neutron stars, an event now cataloged as GW170817. Crucially, this collision also produced light, visible light, X-rays, and radio waves, allowing for the first time telescopes around the world to point at the exact same cosmic event that gravitational wave detectors had just registered, confirming the signal's origin directly. What astronomers found when they studied that light would answer a genuine open question in physics that had lingered for decades. For a long time, astronomers understood reasonably well where lighter elements originate, hydrogen and helium from the Big Bang itself, and progressively heavier elements up through iron forged inside the cores of stars, exactly as we've described on this channel before. But elements heavier than iron, gold, platinum, uranium, require a process demanding far more energy than ordinary stellar fusion can supply. Where, precisely, did they actually come from? The collision of 2 neutron stars, it turns out, is one of the primary answers. When GW170817's 2 neutron stars merged, the collision briefly created conditions violent enough to trigger what physicists call the rapid neutron capture process, nuclei absorbing neutrons so quickly that extremely heavy elements form within a fraction of a second, far too fast a process to occur inside any ordinary star. Telescopes observing the aftermath directly detected the specific light signature, called a kilonova, matching the theoretical prediction for exactly this process, and calculated that the collision likely produced several times the mass of the Earth in heavy elements combined, including a genuinely significant quantity of gold and platinum, flung outward into interstellar space by the force of the collision. Some fraction of every gold ring, gold coin, and gold circuit board on Earth almost certainly traces its origin to an event like this one. Two ultradense stellar remnants, colliding somewhere in the ancient universe, briefly outshining entire galaxies, before scattering their newly forged elements across the cosmos. GW 170817 mattered for a reason beyond even the gold. It marked the beginning of what astronomers now call multi-messenger astronomy, studying a single cosmic event using multiple, entirely different types of signals simultaneously: gravitational waves, visible light, X-rays, and radio waves, each carrying different information, together painting a far more complete picture than any single method could achieve alone. Before 2015, humanity's entire understanding of the universe rested on studying different forms of light: visible, radio, infrared, X-ray. Gravitational waves opened a genuinely new sense entirely, allowing astronomers to essentially feel space-time itself flex, in addition to watching light arrive. Neutron-star mergers, precisely because they produce both gravitational waves and visible light together, sit at the exact intersection of these two ways of observing the cosmos. Since GW 170817, observatories have detected additional gravitational wave events, steadily building a catalog of cosmic collisions, merging black holes, merging neutron stars, and possibly mixed pairs of both, each one adding to our understanding of how the universe's heaviest, densest objects behave when gravity finally, violently, brings them together. Somewhere in your jewelry box or in the wiring of the device you're using to watch this, there is very likely a small piece of two neutron stars that collided long before Earth existed, flung across the galaxy, gathered by gravity into the cloud that eventually became our solar system, and finally mined, refined, and shaped into something you now own. The universe, once again, turns out to be inside you. If this story moved you, subscribe to Cosmic Horizons. The universe is full of stories like this one, and we tell a new one every day.